In my notes, you will actually see an interesting example of how I can actually create an inductor out of a sorted transmission line. And so I want to show you here just the highlights of this calculation. So let's go back to the equation I gave you before for the Z in. So this was JZ naught tangent beta L. And let's assume that my length is very small. So let's assume that I have a sorted transmission line, but this sorted transmission line is also pretty small. It's pretty short. So we are talking about moving away from a sort at some distance L that is much less than lambda. Or equivalently, my beta L, which is the electrical length we discussed before, will be much less than 2 pi or much less than 360 degrees. Now, what does much less mean? Well, much less is really up to you to make the approximation we'll make in a second as accurate as possible. But I will say typically this equation this approximation is quite good up to, let's say, 1/10 of that. So maybe up to 36 degrees or so. And maybe you can push it up to 45 degrees maximum. After that, really, the approximation starts becoming not very accurate. But nevertheless, if I do have a sorted transmission line and I just move a little bit away from that sort, then I can essentially make the approximation here that this is equal to JZ naught beta L. So in other words, I replace the tangent with its argument. And essentially, if I replace now my beta with, let's say, the transmission line and omega, so this can be written as Z naught L divided by V. So what is really interesting about this equation is that I started with a sorted transmission line. I was able to express tangent beta L as approximately equal to beta L. And then I replaced beta, and I got this equation here, which can also be written as J omega times some effective inductance. I mean, at the end of the day, what is the impedance of an inductor? The impedance of an inductor is J omega times some value, while this value of the inductor is equal to Z naught L divided by V, the speed in the transmission line. So essentially, that means that it is possible for me to create an effective inductance, L effective, which be equal to Z naught L divided by the phase velocity V. And if I go just one step further, I can express my Z naught as square root of L by C, square root of impedance of inductance per unit length over capacitance per unit length times L divided by the phase velocity, which is 1 by the square root of LC, as we discovered last time. So if I look at this equation here, that means that my effective inductance that I get from this equation is equal to nothing else but the inductance per unit length, L, times the length of the line. What a beautiful result. It's actually one of the simplest inductors you can ever make. It's simply a short section of a transmission line, and you'll get this very beautiful result that approximately it's equal to the inductance per unit length times the actual length that you have. And it's a very intuitive result. It's exactly what we would have expected, and that's exactly what happens. But on top of being a beautiful result, what is really important to recognize here is that this is actually a very good inductor. What I mean by a very good inductor is that it has a very good quality factor. Now, you may remember from your undergraduate days what a quality factor is. Just to remind you, a quality factor is a number that tells you how effectively the inductor stores energy and doesn't lose it. It's really difficult in high-frequency circuit design to actually get good high-quality inductors. A lot of times, if you make an actual coil, the Q will suffer. And there's a lot of research work that shows technologies that make good high-quality inductors using coils. And those results are fantastic, but it does take quite a bit of complexity to achieve that, versus the technology we're looking here, where essentially you just take a short transmission line length, and there you have the inductor is there. That's the advantage of this. Now, what's the drawback? The drawback is that for a large inductance, you really need the large length. So this L is going to end up being a very large number, which is bad because it does take a lot of space. So that's not nice. That's not really effective in many circuit design approaches because space on an integrated circuit is important, is expensive, and so we don't want to make that happen. Needless to say is that if you make L too large, perhaps this approximation here won't be true anymore, this approximation right here. And so that means that there is a limit, both from a mathematical perspective as well as from a cost design perspective of how large of an inductor you can actually get from this technology. So again, the main result here is that it is possible to get a good quality inductor out of a short transmission line, but it's not easy to get a high value, a high inductance out of this approach.